The late Jurassic was an age when massive sauropods filled the grasslands, stegosaurids roamed in heavy armor, and predators no other creature could challenge prowled in the shadows of endless forests. At the very top of this world stood Allosaurus and Torvosaurus, with razor-sharp teeth and jaws powerful enough to crush bone. They were not just hunters, they were the very regulators of the ecosystem's balance. But the fossil layers reveal that this magnificent scene changed abruptly. In the Morrison Formation and other rock sequences from the same period, the remains of these two apex predators suddenly become scarce and then vanish entirely. There is no gradual decline. It's as if a page in history abruptly closes and their names no longer appear on the next. This disappearance aligns across the records of not just one region, but a vast stretch of land. So how did the rulers of the late Jurassic vanish in such a short time? Before we search for the answer, we need to take a closer look at their world. Allosaurus was one of the most agile apex predators of its era, reaching an average length of 28 feet and a weight of about 2.5 tons. Its muscular hind legs were perfectly built for chasing prey at high speeds, while its long, powerful tail acted as a counterbalance during sudden turns. The skull, with its flexible internal joints, could shift slightly to the side while biting, allowing its sharp teeth to cut deep from different angles. Each tooth, serrated like a saw blade, was sharp enough to slice through bone, tearing muscle tissue and causing severe blood loss. Its bite strength relied less on sheer crushing force and more on the lethality of the wounds it inflicted. Prey was often not killed outright, but weakened and exhausted through blood loss. This strategy points to Allosaurus as a patient and tactical predator. Torvosaurus, on the other hand, had a very different hunting style. Measuring over 33 feet in length and weighing around 3 tons, it was larger in build, slower, but an unstoppable force. Its skull had fewer teeth than Allosaurus, but their roots were much deeper, making them almost impossible to break. Its jaws could deliver a sudden, powerful snap capable of crushing the bones of its prey. While its forelimbs appeared short, they were packed with strong muscles and ended in inward-curving grasping claws. Once these claws closed around prey, they acted like a vice, leaving virtually no chance of escape. Both species sat at the very top of the food chain. Their prey included long-necked giants like Diplodocus, heavily armored stegosaurids, and smaller herbivores. Tooth marks in the fossil record show that they were not only active hunters, but also opportunistic scavengers. There is still debate over their hunting behavior. Some evidence suggests they may have formed cooperative groups like modern lions, with adults taking the front line to slow, massive prey while faster, more agile juveniles delivered the killing blow. On the other hand, some paleontologists believe they were solitary hunters, forming only temporary alliances when they crossed paths. Although the multi-individual fossil sites in the Morrison Formation have yet to yield definitive proof of which behavior was dominant, the variety and age distribution makes division of labor-based hunting strategies seem more likely. With all these traits, Allosaurus and Torvosaurus played a major role in the late Jurassic ecosystem. Their presence shaped not only the population of their prey, but also migration routes, the balance of grasslands, and even the territorial ranges of other predators. Yet this seemingly robust structure was fragile enough to be shaken by the introduction of a single variable. To trace the signs of that critical factor, we need to take a closer look at the geography of their world. The world they inhabited was entirely different from the current distribution of land and sea. During the late Jurassic, Pangaea still existed, but the massive supercontinent was irreversibly breaking apart. This slow but steady separation opened new seaways along continental edges, allowing ocean waters to push deeper inland. The process created long, narrow marine channels along the coast, while in the interior, vast and deep subsidence basins began to form. Most of the landmass stretched along the equatorial belt, where miles of arid deserts were sharply divided from humid forest valleys. In some places, this boundary was so pronounced that with a single step one could move from red, sun-baked soil into the shaded, moisture-rich canopy of a dense ecosystem. Along the coasts, wide tidal flats and marshlands formed under the influence of the tides, creating rich habitats where marine and terrestrial life met. The climate followed a cycle in which warm, humid periods alternated with dry spells. Monsoon-like rainfall patterns led to the formation of seasonal lakes in some regions, while others endured prolonged droughts. This climatic mosaic directly influenced the migration routes of herbivore herds and, in turn, shaped the hunting strategies of predators. One of the most notable effects of Pangaea's breakup was the gradual retreat of the Sundance Sea, a shallow inland sea that stretched across what is now western North America. For millions of years, it had penetrated deep into the continent, creating swamp ecosystems, coastal lagoons, and vast deltas. By the late Jurassic, however, the sea began to slowly withdraw, leaving behind expansive alluvial plains and grasslands. This transformation altered not only the vegetation, but also the migratory paths of large herbivores. As the grasslands expanded, long-necked sauropods moved toward these new feeding grounds, which in turn reshaped the hunting territories of Allosaurus and Torvosaurus. Climate was, therefore, one of the most important factors defining the boundaries of this ecosystem. Coastal areas remained humid and mild, while the interior was dominated by deserts with pronounced seasonal temperature differences. Monsoon-like seasonal rains periodically flooded certain regions, only to be followed by months of drought. These transitions caused fluctuations in vegetation, and consequently, seasonal rises and falls in herbivore populations. The ranges of Allosaurus and Torvosaurus increasingly centered on the zones where these climatic mosaics met. Open grasslands provided ideal conditions for using their speed and long-range vision, while forested valleys offered excellent cover for ambush. But the retreat of the Sundance Sea and the breakup of Pangaea brought more than just geographical changes. The geological forces at work beneath the surface triggered far more dramatic events. As tectonic plates shifted, the subduction of the Farallon Plate beneath the North American continent set off a new geological phase. The Nevadon orogeny, a mountain-building event that unleashed continuous volcanic activity across hundreds of miles. Rising magma accumulated into massive cones, and eruptions from these volcanoes released ash clouds dense enough to darken the skies for months. Carried by the wind over thousands of miles, this ash mixed with rain to form compounds such as sulfuric and nitric acids, producing acidic rainfall. These rains burned plant leaves, altered soil chemistry, and disrupted the pH balance of freshwater lakes. The impact on ecosystems extended far beyond physical destruction. Thin layers of ash, still visible today in the Morrison Formation, testify to the scale of these eruptions. Some of these layers contain toxic metals such as arsenic, mercury, and lead. These elements were first absorbed by plant roots, then accumulated in the tissues of herbivores, and finally spread through the entire food chain to predators. The pressure from climate and habitat changes first became apparent among the herbivores at the base of the food web. The loss of grasslands, altered migration routes, and unreliable water sources caused a sharp decline in the large herbivore populations. Giant sauropods like Diplodocus were forced to travel longer distances, while armored stegosaurs adopted more defensive behaviors as their habitats shrank. The drop in numbers of these animals, primary prey for the apex predators, directly reduced the survival chances of top hunters. The collapse of the food chain also disrupted the balanced functioning of the ecosystem. The decline of large herbivores slowed the regrowth of vegetation, which in turn increased erosion and reduced the quality of water sources. This breakdown in plant and water cycles further weakened the remaining herbivore populations, tightening the shrinking circle in which apex predators could survive. With competition intensifying, conflicts among large predators became inevitable. Shrinking hunting grounds, declining herbivore populations, and imbalances in the food chain often drove top predators like Allosaurus and Torvosaurus to pursue the same prey. Such encounters were rarely limited to short, non-lethal chases. Deep and irregular bite marks found on some Allosaurus bones in the Morrison Formation are fossilized evidence of these clashes. The fact that most of these wounds showed no signs of healing in the bone tissue indicates that the attacks often resulted in the victim's death. These struggles were not limited to confrontations between different species. Individuals of the same species, particularly adult males, also fought directly over food resources and mating rights. Under scarce food conditions, these battles became even more intense. Injured or weakened individuals became targets for rivals and were sometimes killed and consumed by stronger members of their own species. Such intraspecific cannibalism was more than opportunism. It was a sign that the ecosystem was under severe pressure and that predator populations had reached a stage where they were consuming their own kind. The death of a single individual reduced genetic diversity, lowered reproductive potential, and slowed the population's recovery rate. In an ecosystem where competition has intensified and food sources have dwindled, weakened populations also become vulnerable to invisible enemies, diseases, parasites, and biological disasters capable of deadly effects. Fossil records cannot preserve the biological material needed to directly identify a virus or bacterium, but abnormal bone growths, unhealed fractures, and signs of inflammation on bone surfaces offer indirect evidence of a weakened immune system. Some Allosaurus bones show deformations that bear the marks of chronic infections or metabolic disorders. Such health problems reduce hunting efficiency, lengthen recovery times, and make individuals more vulnerable to predators or starvation. As in modern predators, individuals forced to roam vast areas in search of prey are more likely to congregate at water sources or carcasses, creating ideal conditions for disease transmission. In addition, heavy metals such as arsenic and mercury, released into the atmosphere after volcanic eruptions, may have further amplified this biological pressure. Absorbed by plants, these toxins pass to carnivorous predators through herbivores. This chain of contamination could suppress immune function, lower reproductive success, and rapidly weaken resistance to disease. Parasitic pressure was also among the possibilities. In warm and humid regions, an increase in blood-feeding arthropods or intestinal parasites could lead to long-term energy loss and fatal infections. Even in modern ecosystems, predator populations living at high densities create an ideal environment for parasites to spread rapidly. In reality, disease and biological disaster scenarios alone do not provide a complete explanation. However, in a population already weakened and struggling with hunger, they could be among the fastest mechanisms capable of causing lethal effects. When all these pressures converge, new species emerge that could quickly fill the vacant top predator niche in the ecosystem. Some dromaeosaurids and ceratosaurids that appeared during this period gained an advantage through their agility, quick reflexes, and flexible hunting strategies despite having smaller bodies. They were not dependent on large prey. Instead, they could target smaller herbivores, juvenile sauropods, and, when the opportunity arose, carrion. These new competitors stood out not only for their speed, but also for their behavior. Dromaeosaurids, moving in small groups, could use coordinated attacks to hunt prey that even larger predators struggled to bring down. Ceratosaurids, on the other hand, specialize in armored prey thanks to their powerful jaws and robust teeth, making them direct competitors for some of the primary food sources of Allosaurus and Torvosaurus. Fossil records also provide evidence that this competition was not merely indirect. Broken bones, healed bite wounds, and tooth marks from different species point to physical confrontations between predators. Such encounters could have led to fatal injuries or long-term disabilities for large predators already struggling to survive on low-energy reserves. The evolutionary consequences of this competition are equally significant. Smaller, faster predators adapted more easily to rapidly changing climate conditions and fluctuating prey populations. Species like Allosaurus and Torvosaurus, with high energy requirements and hunting strategies focused on large prey, were more vulnerable to these shifts. Within just a few generations, the role of apex predator in the ecosystem had completely changed hands. The balance once dominated by Allosaurus and Torvosaurus was gone, replaced by a very different power dynamic. A similar transformation took place among herbivore communities. As the numbers of giant sauropods declined, shorter-necked and faster reproducing iguanodontids, along with small ornithopods, became more common. The growing diversity in plant life supported the adaptation of these new species. Transitional zones forming between open grasslands and forested areas provided abundant resources for both predators and prey. But how do we read the traces of this dramatic transformation millions of years later? Current theories can partially explain why Allosaurus and Torvosaurus disappeared, but bringing all the evidence together into a single, complete framework is still impossible. By nature, the fossil record is limited, leaving us to read this story with missing pages. Remains preserved in geological layers form only under specific conditions and in certain locations, making it impossible to fully reconstruct the ecosystems of millions of years ago. Even in fossil-rich sites like the Morrison Formation, only a small fragment of the original record has survived to the present day. To fill these gaps, researchers are using increasingly advanced methods. Isotope ratio analysis in bones provides clues about diet and migration routes. 3D digital modeling techniques make it possible to reconstruct details ranging from the healing time of fractures to predator-prey interactions. Geochemical scans can deduce past atmospheric conditions from the composition of volcanic ash layers. Fully uncovering the details of this ecological transformation from millions of years ago may one day be possible through new technologies and yet-to-be-discovered fossil sites. But there is one thing we know for certain today. The rulers of the late Jurassic vanished from the world stage, leaving behind traces that still defy explanation.